All right, everyone, let's get started. Who's excited to go back to EM? Who wants to just move past it? Okay. So I added some new slides because I felt like maybe it could be explained slightly better. So I'll give a recap of where we are, and I'm going to use some of the same slides, but I added a few diagrams in that maybe help a little bit. Okay. So last class we introduced this notion of clustering, which is unsupervised learning where there are no labels. We just have these data points X. And then we'd say for some fixed number of clusters K, let's find these clusters. And we saw this very popular algorithm called K-means, which is an example of a centroid-based clustering algorithm that just had these like centroids, which are vectors of the same dimension of the space as the points. And then we kind of went through trying to just think about what it's doing and what maybe some of the problems were, and worked our way towards a probabilistic model. On the way there, going to this soft K-means to try to understand about having soft attribution of each cluster for one point. And so, but eventually what we ended up with was this mixture of Gaussians, which is sort of a proper probabilistic model that lets us understand our assumptions and also let us actually turn the crank of maximum likelihood estimation. And so these are also one of the simplest examples of what in statistics and machine learning are called latent variable models. And in these models, we introduce purposely what we call as a latent variable. So it's a variable we don't have observations for. And for the mixture of Gaussians, it was these Z. And so I apologize because I've taken little snippets from here and there. So some of the notation might be going back and forth. There's a question last time that this was the power end. This is the nth data point. If you're ever unclear, please just ask me. And so each observed data point has associated with it its own latent variable, and that latent variable refers to, for the mixture of Gaussian model, it refers to which cluster it belonged to. So it's a discrete variable that could have the value 1, 2, 3, up to k, and we're never going to know it exactly, right? So we're going to estimate the probability that z is equal to 1, 2, 3, all the way up to k. And so the reason we do this is that by introducing this latent variable model, we can often write down the likelihood can kind of factor in nice ways, and we get sort of these decomposable models that are a bit easier to think about. And it also turns out that even though we could turn our crank of just regular gradient descent optimization, for these kinds of models, for many of them, we can use this algorithm called expectation maximization, which is particularly for likelihoods structured with these kinds of latent variable models. So you can't always do it, but you can do it in many cases, and by the end of this, you might be able to get a feel for when you can and can't do it. Right, and so this algorithm is actually used all over the place. You may have heard of models called hidden Markov models for time series data. They come into computational biology and speech and all kinds of places. These typically are trained using EM. So it actually is useful in its own right, and it also does form the basis for more advanced topics in machine learning, and in particular variational inference, which I'll just give you the slightest hint of a taste of what it is on one of the slides near the end. And if you want to learn more about it, I've got a pointer as well to something you could read. So, okay, so remember that the log likelihood is really easy to write down if we assume the existence of these latent variables. This is one of the reasons we introduced them, right? So we basically just have to marginalize it out because we don't know its value. So we sum out its value. And when we do that, it looks like this, where this alpha is a parameter that just represents the probability, the prior probability that any particular point belongs to cluster K. And then we're basically just saying how much does it belong to each one, weighted by its probability. And so also there was a question last class, and I actually had defined this, but I've tried to now cut and paste this on the slides so that we don't lose track. But I'm going to use this data just as a general thing for all parameters. And so with the mixture Gaussians, it'll be these three parameters. But EM is, of course, applicable well beyond the mixture Gaussians. So when I'm talking about it in the general sense, I'm going to sometimes just use theta so that it's clear it's a very general algorithm. So, okay, so I'm going to try and go through again the intuition of the updates with some pictures this time and just try to reinforce what I said last time. And then I'm going to try to quickly go through some of the proof we did towards showing that it's maximum likelihood estimation and try to give you an idea of how you can derive your own EM algorithm for different models. Are there any questions so far? Okay. Okay, so I found these, there's a cute video that someone had created these pictures for. So in the E step, we're going to somehow initialize, as we would with a mixture of Gaussians. You can either initialize the E step or the M step, whichever one, then you start with the other one after that and you iterate back and forth. And the goal in terms of statistics of the E step is precisely to compute this posterior here. And what is this posterior intuitively? It's the probability that for the nth data point, its latent variable, that is its cluster assignment, is equal to K. And we want to compute that after we've looked at the data point itself and based on the parameters that we have, the current parameters in the algorithm. Does that make sense? So in some sense, it's just saying you use the rules of statistics, like we're going to use Bayes' rule, as it turns out, to compute how much you believe from the data and the parameters that each point belongs to each cluster. It's like a pretty simple concept. Okay, so that's the goal. And then I showed you some slides, and maybe it's easier to break it apart a bit, so I've added some text now. So one way to think about computing this, like just remember that's the goal, is to first think of getting sort of like a score for each Gaussian. So how much does, like we're considering one point, the nth point. So how much, oops, I think that should have an n there. Fix it right now. So no, it should have a, I see, in the case of mixture Gaussians, it's an n, which is written below. Okay. Easier to fix it while I'm lecturing, then I don't forget. Okay, so we're gonna first just compute the score, which is really just how much does the density of that point evaluate under the Gaussian, in the case of the mixture of Gaussians. So I'm gonna instantiate with that as the running example. But really we're just computing this probability. In the general form, when it's not a mixture of Gaussians, is how much do I belong to like the kth component. And then I'm going to use Bayes' rule. I have to fix this in utopia again, whatever. Okay, then I'm going to use Bayes' rule to go from there to compute the desired posterior that I want, right? So Bayes' rule lets us go from probability of z given x to probability of x given z to z given x, except that x here, well, it does depend on z through k here, right? And so we get these things, which are just the sort of score up above, times the prior probability that it belongs to each cluster, and then we have to normalize it to get a probability, which comes out of Bayes' rule. And when you plug in this is a shorthand, just to like, it's convenient if you're coding to maybe use these shorthands, then it looks like this, which is the update I put in the slide last week. And this is sometimes in those slides, people often refer to these as like items or parts of the Q distribution, which came in when we're trying to prove that it's maximum likelihood estimation. So that's just why this ends up being called Q. So P is sort of the unnormalized amount of how much it sort of belongs to each Gaussian according to the density, and then Q is after we've kind of flipped it around and used Bayes' rule. And so the E step really is just using, again, the rules of statistics to compute this posterior. Any questions on that? Yep. I lost the cursor. Ah, you should like yell that out. Okay. Otherwise I'm talking to myself. All right. Okay, that's an easy one.
Do we know the distribution of the data? What if I have no idea of how they're not like, well, the data's not distributed?
I mean, so that's, I mean, in general, you don't know the distribution of your data, and so Gaussians are pretty general, and if you mix a bunch of them together, then you can capture quite a rich set of distributions. So the idea with mixture of Gaussians is that you don't know that they're Gaussian, but you hypothesize that using a mixture of Gaussians is a rich enough representation that you could capture it. But that may not be the case. So in general, this is how machine learning goes, is you make some assumptions, and you think it through, is this reasonable or not, or you have a lot of practice doing it, and you know that that tends to work well, but you might want to do something else also. Yeah. And so, when we teach these things, like I'm not saying you should always use a mixture of Gaussians. We can't teach you everything, and the things we choose to teach you are often just good pedagogical tools to understand some of the general principles instantiated in a particular form. But these are actually very common models, and these are used quite a bit. Okay, so that's the E step. And then, and so in this example, it's a one-dimensional Gaussian. K is equal to 2, there are two Gaussians, a yellow one and a purple one. And so this is how they are at the very beginning. And during the E step, there's a whole bunch of points lying on the real line here. And each one you can see is colored partly yellow and partly purple. And the color here is meant to denote the value of the posterior. So the posterior is going to tell you how much you belong to yellow and how much you belong to purple, and it's going to sum to 1. Right? That's the definition of a distribution. So this guy is sitting almost in the middle of the yellow, so it's kind of very yellow, but he's also kind of sitting quite purple, so he's also got quite a bit of purple, but a bit less. And as you move further and further away, it's pretty clear that first of all, this guy probably doesn't belong to either of those Gaussians, but if you had to pick one, it's obviously going to be the purple one, right? So that's why this guy is like completely purple. And so this color here is meant to be like a color code for the posterior of it being yellow versus purple in the case of K equals to 2. Does that make sense? That's basically the E step is just computing for each point, again, like a probability that belongs to each one, and those probabilities sum to 1. And they're doing it by looking at the distributions. They're looking at the mean, and they're looking at the covariance, and deciding that. Okay, so in the M step, we've assumed we've already done an E step, because whenever you do one, you assume the other one's been done. And the goal is now to use those somehow to update the parameters of the model. And so in general, that's theta for the mixture of Gaussians. Those are all the means, the covariances, and these things we call the mixing weights, which are the prior probability that you belong to each Gaussian. Okay, so the thing to note is that if you knew in the mixture of Gaussians, if you already knew the value of those latent variables z, then that would tell you which cluster they belong to, right? Like that's kind of the thing we're trying to figure out. But if you knew it, it'd be very easy to compute these parameters, because everything would decouple, right? You would take all the points that you know belong to cluster 1, and you would just compute its mean and its covariance using those points. And then you'd basically be done. And there'd be something just as trivial for these mixing weights. You would just say how many, like if 30% of the points were in the yellow and 70% were in the purple, then the mixing weight would be 0.3 and 0.7. So do you see that if you knew the value z, it'd be really trivial to update the parameters, right? Any questions on that comment? Because it's like kind of a key insight of EM, is if you knew those things, it'd be trivial to get the parameter updates. But of course we don't know them. However, we have something very close to it that we just got from the E step, right? So instead of knowing that it was purple or yellow, we know kind of fractionally how much yellow or how much purple it was. And so we can, instead of doing standard maximum likelihood estimation for each Gaussian, we do it by weighting the samples by their posterior. And so by these, essentially these things down here. And so, right, and so what that's going to look like is, again, this is basically, if you were to compute the mean, normally you just sum up all the data points and divide by n, but here we're doing it in this softly weighted way, where it's sort of softly weighted by the posterior, where this is always between 0 and 1. And so now the update, instead of the standard mean update, would look like this. Any questions? Okay. And so it's all, I think I mentioned this last time, but it's good to also think about, like, well, I've written it with these sort of soft labels, but can I recover regular maximum likelihood in the case where I did know the z? I said, what if, like, I actually knew the z and they were just 0, 1, there was no uncertainty? Well, if you plug that in here, what you get out is, in fact, the standard maximum likelihood update for the Gaussian, and that will be true for all of these m-step updates. It'll be true also for the covariance as well. And so, in fact, so these are the 3 updates you get, and we'll go later through how you would derive these, right? Right now I'm just telling you a recipe to give you the intuition. So this is just what I had written over here, except now it's got a t on top to denote the iteration t. So it's saying at the t+1 iteration, use the e-step posteriors to do a weighted maximum likelihood of the x's to get the mean. And you can see this is right. This is just a formula you would get to compute a covariance matrix, only it's been soft weighted by the posterior again. But you can see this is a very familiar form, right? And then here it's basically just summing up again, like how much how much weight in total each of the k clusters is getting. So what does that look like with this picture? So in this picture now, I'm going to move the yellow and the purple. I'm going to move their means, and I'm going to change their variances. This is 1D. And actually, this picture doesn't show the third parameter, but that I think you get the intuition anyway. So once I compute these updates, and to plug in Q, I'm using these things here, right? Whether how much yellow, how much purple it was for each one. So at this point here, it's not going to enter into the mean estimate of the yellow, because it has no yellow, so its Q will be 0 for that. It actually does have a 1 for purple, and it has a 0 for the other one. Does everyone see that? That this point will not affect the mean update of the yellow. In contrast, this point is going to affect both the yellow and the purple. It'll affect the yellow one a little bit more because its weight will be a bit higher than the yellow one. And as I go further this way, the points will increasingly only affect the purple one. And so once I apply these updates, then I move the mean and I change the covariance, and in particular in this way. So this mean gets shifted a little bit to the right because all the points that are assigned to it are a little bit to the right. So it makes sense that it's going to move a little bit to the right, but it doesn't move very far to the right because really only 2 points, more or less, are actually influencing it, right? The ones that have some amount of yellow. And in fact, it's mostly this one. And the purple one, on the other hand, it moves quite a bit because all of these points it's trying to take responsibility for. So it has to move quite a bit. Moreover, because those points are really spread out, it has to spread itself out also to get them. Whereas that yellow one's really only taking care of 2 points, so its variance doesn't really change. It mostly just gets shifted over a little bit. Is that intuition now of the E and M? Is this better than last lecture? Does it help a bit? Okay, awesome. And then there's a video. I have the link. You can watch a video of someone also explaining this if you want. Okay, any questions on that? So that's the intuitive recipe for mixture of Gaussians, and for EM, instantiated with mixture of Gaussians. Okay, so right, just we put it all together. This is what it is. It's the E step, compute the posterior using Bayes' rule, which gives you the value of these dots, and then the M step is to update the parameters of the model. So E step again is just, this is just shorthand notation for the posterior, and then it's those updates I just showed you. So that's, and this is it evolving. So this is after another iteration, yellow is actually reclaiming more responsibility, so its variance gets wider and it shifts over some more, and then the purple looks like this. Ooh, okay, so I try to animate these so there's not like a whole wall of text, but okay, there is. So, right, that was a recipe to give you the intuition, and again, just trying to emphasize the intuition here is you're kind of completing those missing data, those latent variables, the things you wish you knew, by probabilistically assigning things via the posterior. And then the M step, you're doing posterior weighted maximum likelihood estimation. And then you iterate until convergence. And so, right, so I just told you this. I haven't shown you that it performs maximum likelihood estimation. We started to work our way there last time, and that's where I started to tell you about this viewpoint that's something called the free energy viewpoint of EM that comes in handy. So it's not the only viewpoint. Actually, probably in more classical statistics lectures, you wouldn't see this, but the reason I'm giving you this viewpoint is it forms the basis for a lot of advanced machine learning. So if any of you want to go on and learn about variational inference and stuff, it's really, really good to have seen it in this particular context. So, right, so how did the proof work? Let me just try and, I'm gonna try and quickly go through some of the stuff we said last time. We said there's this likelihood and it has this annoying log that couples things, like, and we could just do gradient descent, but we can't just get a closed form estimate because of this log. And that log arises from doing marginalization, right, outside of this sum. We have to marginalize out the thing we didn't know. So then we introduced this notion of this thing called the expected complete log likelihood. And really the complete log likelihood is basically the likelihood of the data we have and the data we wish we had. That's why we call it complete, because we've kind of completed by wishing we had the z there. And then when we introduce this arbitrary distribution q, which later on we're going to set equal to the posterior, but in the derivation we don't sort of know that yet. Right now it's just an arbitrary thing. And we say the expected complete log likelihood is just this thing that, like this, that's going to come into the bound that we derive. Okay, so I won't go through the whole thing again, but why is it not trying to, weird. So there we go. Okay, so we went through and basically said you can take the likelihood for one data point and you can go through a series of manipulations and use this thing called Jensen's inequality. And in the end, what you do is you end up bounding the likelihood. So the likelihood is always greater than or equal to the entropy of this so far arbitrary Q distribution and the expected complete log likelihood. And this bound is going to turn out to be useful because we're basically going to maximize the bound. And by maximizing the bound and occasionally satiating the bound, we'll actually be doing maximum likelihood estimation. And so in particular, this bound, and I will I think prove this on the next slide, is so right now, again, Q is an arbitrary distribution. If I plug Q in over here, so I plug the posterior in for Q, then this greater than or equal becomes an equal sign. And in that case, the bound is actually, it's not a bound, it's exact equality. And so that's going to be useful. That means that as we are maximizing the bound, if we sometimes set Q equal to the posterior, then we actually have the likelihood. And that's going to allow us to constantly increase the likelihood. Okay, so right, the claim I just said was that when Q is equal to the posterior, then that bound becomes satiated, which means the likelihood is equal to this thing called the free energy. And so you can just kind of plug things in. So this is what we call the free energy. It was the entropy of Q, but now I've plugged in P. And then it was the expected complete log likelihood, where actually this should be a P as well because I'm plugging in Q for P. And then I can just take the definitions of the entropy, which we already went through, and the expected complete log likelihood, which I just described. And if you put those both in, this is what it looks like. And then you just keep going with the math. So now I'm just rearranging these terms. I don't know, is that skipping a step or is that obvious? Oh, I see. Yeah, I'm just saying that this blue thing is equal to this divided by this, right? You can see that because this is a joint of x and z. I can always get the conditional by dividing by the x. So this is equal to that. It is obvious to see. And then I can keep going. I can pull this out now. And so let's see, is this one obvious? Log. This one may not be. So okay, it might be skipping some steps here because this doesn't seem obvious to me. But if anyone has trouble or wants me to expand that out, let me know. And you do end up getting the likelihood. So what that means is even though I've created this bound, which depends on some arbitrary distribution Q, when you plug Q in, you get the exact likelihood. Okay, so how are we going to use that? Again, this is the bound, and basically what we're gonna do is we're gonna take this thing called the free energy, and we're gonna first optimize it with respect to Q, and then we're gonna optimize it with respect to theta, and go back and forth. It's gonna be like an alternating coordinate ascent. And every time we optimize with respect to Q, what we're gonna really do is just set it to the posterior, and when we do that, this is gonna be an equality, and we'll actually have the likelihood. So as long as we keep increasing F, and we keep setting Q equal to the posterior, then we're guaranteed to keep increasing the likelihood. And so that's basically kind of in words, how you get to the fact that this is always increasing the maximum likelihood, or say the likelihood, and therefore, once it converges, you've arrived at a local maximum and done maximum likelihood estimation. So sometimes people plot it in this way, which is, so first in the E step, you're finding the Q, that is the maximum of the free energy. And when you do that, after you've done that, then the free energy is actually exactly equal to the likelihood. And so, right, that's just computing the posterior. And so you can just think of this thing as having like 2 dimensions, like a kind of Q, which is distribution, and theta, which is a set of parameters. And you're just gonna optimize in one, and then in the other, and in the other, until you get to the optimum of F of Q and theta. And then at the very end, you do one more E step, and you have the exact likelihood. So, and then in the M step, you're gonna take the argmax over theta of this thing. And when you do that, then you know, once you've completed this, you no longer have satiated bound because you've changed theta. So even though it was the correct posterior at the previous step, you've now changed theta and it's not. So now you are operating with the bound again. Only after each E step do you actually get the likelihood of that. But you keep increasing F, right? Always increasing F, and every time you do an E step, you're getting the likelihood. So it means you're always increasing the likelihood. And just another way to visually look at it, in addition to this one, is if this is now on this axis the likelihood, and this is like the parameter space. So the bound is just satiated. So we just did an E step, and this is the current value of the parameter, and we know it's satiated because we're on the likelihood surface here. And then basically to find, and so now we have a new, and now we can create like a new lower bound as a function of theta, and then move to the next best theta, which will be over here. And then we can again do the E step, which will take us up to the likelihood. And so it's basically what you're doing is every time you're on the likelihood surface, you're creating like a local kind of lower bound, going to the top of it, and then satiating it by doing the E step. So this is, it's kind of, I agree this isn't sort of like, I think this would be hard to absorb in this lecture, but I think it's really good for you to have seen it, and so there's a lot of interesting stuff going on here. Right, okay, so that's somehow saying that if I think of EM as doing coordinate ascent on the free energy, on theta and on Q, then I have a guarantee of maximum likelihood estimation. And so I can also just use this framework in addition to showing that it's maximum likelihood estimation. I can also use that framework to derive these updates, right? So far I just told you these were the updates. I said compute the posterior and compute the M steps in this way. So how would you actually use that bound to do it? So remember, this is the bound we have. And so in the M step, what we're doing is we're optimizing the theta parameters given that we have a value of Q. So given that we already have a value of Q, this dependence on theta falls out, and we only need to look at the expected complete log likelihood here. And when we do that, so we write down that expected complete log likelihood, because again, the parameters don't appear here because we've already computed Q. So they did depend on it through Q, but we've computed Q. So it's basically depending on the previous parameters. Then, as we do all through the course, we take that thing, we take its derivative, and we set it to 0. And it turns out for things like the exponential family, which the Gaussians are included in, you get a closed form update, just as you do for like a maximum likelihood for the mean and the covariance in the regular case. Now you also get a closed form update, but it's these things weighted by the posterior. So the upshot, right, is that you get these posterior weighted versions of the standard maximum likelihood estimates. And if you were in a family of things where you couldn't do the exact closed form maximum likelihood, you could instead just take a gradient step in the right direction. Instead of doing a complete update, you could just move partly in. I don't have this in the slides, it's sort of more advanced, and this is called generalized EM. And so, right, just to emphasize, these Q kind of filled in the missing data that then, when we turn the crank through all this, what we end up doing is doing weighted maximum likelihood with these filled in data. And that's where it comes from. It's from this sort of expected complete log likelihood in this formulation. And so again, if we had certainty on these Q, then it would just reduce to the standard MLE for all the points belonging to that component. Okay, and so really what you would do, someone gave you a Gaussian, and I said, like, sort of formulaically, I said, we don't have a dependence on this, we have a dependence on this for the parameters, so let's write it out and let's take the derivative, right? So for mixture Gaussians, this is the expected complete log likelihood. If you go back to the definition, you can do that at home and you can write it out. This is exactly what it is. And then now we want to, again, we assume Q is fixed because we've done an E step. And then we literally just take the derivative of this thing with respect to the parameters we're interested in. I only showed 2 of them here. And then you can set this to 0 and solve it in closed form. And that's where those updates came from. So if I gave you a different model, which was not a mixture of Gaussians, but was like some other kind of density, you would do the same thing. You would first write out the expected complete log likelihood for that wouldn't be a Gaussian, it would be whatever kind of components you're using. And then you would take the derivative with respect to that, and if you could, you would get a closed form update. And if you couldn't do the standard EM. So in standard EM, you would always get a closed form update here, like these ones we saw, these ones, right? These are all closed form. I just say this is the new value. So that's quite a bit maybe to take in. Are there any questions? Confusion, notation, typos, yeah?
Is it always better to use
That's a great question. So we will get there. It's a good question for several reasons. So EM is technically a method to do maximum likelihood estimation. And if I just tell you, I have a slide about this. This is like kind of a pet peeve of mine, so I'm going to go on a bit of a rant about it. So like sometimes I go to places and people say, oh yeah, like I'm working on this problem and this data, and I said, like, what model are you using? I say, I'm using EM. And I said, EM's not a model, it's like it's an optimization method. Like that doesn't tell me anything about what you're actually doing, right? And so like people are not very precise with their terms. So and you contrasted it, and the thing is, the k-means is like a weird object, right? So, and as soon as you go into this sort of ad hoc modeling process where you're not looking at statistical models, it's like, is that the model? Is it the algorithm? Like things get a lot more confused. So k-means is kind of both a model and an algorithm, right? And so I think, like, just to nitpick, to rephrase the question, I think what you were saying, is it better for me to use a mixture of Gaussians than it is to use k-means? Yeah, and so I would argue that yes, always, and I have this in a slide coming up, but basically, I mean, statistical models are principled, they're on the foundation of all of statistics, and we understand what assumptions are being made, and there's all kinds of things that are very well understood, like maximum likelihood estimations. We really know what's going on, and with like these other things are just kind of weird ad hoc stuff, and I could not imagine a case where you would be better off doing that unless you didn't understand mixtures of Gaussians, you didn't know how to code it, and you didn't know how to install a package, and you wanted to code it from scratch, then like maybe, or maybe to teach like your little cousin who's 10 years old, like something like this. And don't repeat that because I think lots of people use it, actually. Okay, where are we? Oh, right, so I was just showing you how you would derive the M step. If you had a new model, procedurally, you would use the interpretation of the free energy, you'd write down the complete log likelihood, take the derivatives, and solve, and that would give you the updates for the M step. I did this in my PhD thesis a number of times. Okay, so the E step, there's not really a derivation here, because we kind of already showed that when I set Q equal to the posterior, then the bound is satiated. So what that means is if I want to maximize the free energy with respect to Q, I just perform this operation, which is I set it equal to the posterior because that's the best I can do. And so that actually just is the E step. And so I won't go through because we already just showed how, this is just Bayes' rule. How do I get that thing? I use Bayes' rule, and then it looks like this. Okay, so I said that this was useful. It's useful foundation also for more advanced models, and just to give you a taste of that, like we won't do it in this class. So this key step here was the E step where we set the Q to the exact posterior. And in the case of the mixture of Gaussians, we could do that using Bayes' rule. Like it was a very simple statistical procedure. But if you go outside the exponential family, then there's many cases where you actually just can't compute this. So in other words, you cannot do the E step. And yet you want to, because you want to be doing maximum likelihood estimation. And so there's a very popular class of models now called variational autoencoders, and this is true for them. So their parameters are not just like the mean and covariance, they're actually, the parameters are actually based on neural networks. So this is a very complicated combination of a neural network with a statistical model and latent variables, and it's kind of crazy. And so in this case, what you do is you don't compute the posterior. What you actually do is you just make a parametric guess of what it might look like. You say, I think it's going to be like a Gaussian, or it's going to be this, and then you actually fit the parameters of it to make it as close to the posterior as possible. And so this is beyond the scope of the course, but that's just to tell you that there's a lot more out there that's based on this. And so if this sounds interesting to you, then you can click on this and read this. Actually, what I send to a lot of people who want to join my group, and I ask them if they know what variational inference is. And so actually, does anyone here, sometimes people read it out, I'm curious, has anyone here heard of a variational autoencoder? So, okay, and I'll tell you that almost every single person that has read about a variational encoder actually doesn't know what variational inference is, and they look at this thing called the variational autoencoder, which is presented in this totally non-rigorous way of an encoder and a decoder, and most people, I would wager a lot of money that of those people put up their hand, they actually don't know any variational inference, and so you should read this, and you'll realize that you didn't understand it. If you did, I apologize, but I bet you didn't. Okay. So, right, and so there was a question about like k-means, and so k-means had these restrictions, right? As k-means, one of the assumptions were not super clear because it wasn't a statistical model, but when we were looking at the objective function, it had this like distance, this square distance, which meant implicitly that the clusters it was forming were spherical. Now with the EM and mixture Gaussian model, we can decide, okay, I want the covariance matrix to only be spherical, I want them to be arbitrary, or whatever. And so this is these are iterations, 1, 2, 3, 4, 5, 6, 7, oh no, actually, sorry, 1, 4, 6, 8, 10, 12. This is before you've done anything, and then you initialize, and as it progresses, so here you've actually initialized it quite stupidly, right? It's not even near the data, really. I guess these must be some level sets of some kind of the Gaussian. And then eventually it gets to here, and you can see these are not actually completely spherical, right? They're a little bit elongated. And so that's one reason, like a very good reason you would not want to use k-means. And again, you could like go in and like hack k-means, right? You could start weighting the different features differently and weird stuff like this, but like kind of like you wouldn't really know what's going on, right? So you may as well just do this. Okay, so then this is, so right, this is my rant. This term is often misused in the way I just described. And so, right, EM is not a model. Mixtures of Gaussians is a model. EM it's not a cost function, such as the likelihood. It does not replace maximum likelihood. I'm writing this all down because I hear these things all the time and they drive me crazy. Right, what it does is it replaces, it performs MLE. Like that's the key thing, is expectation maximization is an optimization algorithm to do maximum likelihood estimation. And as I mentioned, you can generalize it, like we won't go into, to do these partial M steps, and you would still get an exact EM. And I mentioned, so I've alluded to the variational inference, but there's other variations that again we won't go into. So there's something called Monte Carlo EM, where you would represent the posterior with samples rather than with actual parameterized posterior distribution. Okay, so why should we do expectation maximization? I said we could do gradient descent, right? So, and I kind of said partly I'm teaching this to you because a lot of other important stuff is built on top of it. But what about just on its own? So this is not widely known. This is actually quite a funny story. So when I took a machine learning class in grad school, someone asked my advisor, like, why don't you just do gradient descent on the mixture of Gaussians? And my advisor said, silly graduate student, you can't do it because of the latent variables. And this guy now actually runs part of Apple Research. And he said, actually, yeah, you can, and showed him. He said, oh, and then this became a paper that's not widely known, and this fact is not widely known. So actually, as you go on, you'll probably run into people who think that you have to do EM for these models, and actually you don't. So why would you? It's sort of analytically easier to deal with, and it's very simple and intuitive. And so the con is that when you have a lot of missing information, this is a very intuitive kind of hand-wavy thing, but in the sense that the posteriors are very flat, they don't really know where the points belong, then this optimization algorithm can converge sort of excruciatingly slowly, and so that could be a bad thing. And so, in fact, this, right, and when it actually has sort of non-flat posteriors, it can converge super, super quickly, like faster than a lot of other stuff. And so the student, Russ, they actually ended up writing a paper about this from 2003. And actually what's kind of cool is in my research, we actually just made use of this in a paper very recently, which is always fun to dig up old papers, but to do something completely different. Anyway, maybe at some point I'll talk a bit about my research if there's time. But so this is this paper from ICML, one of the big machine learning conferences, 2003, and what they're doing is comparing EM to doing us what they call direct optimization, which is not this specialized structured thing, but just like taking gradients or like a second order. They actually kind of do a second order method. And what they show is that, as I said, when you in certain conditions, like imagine these are the 4 clusters here. You see how they're kind of very overlapping, what they should be. These are the clusters you want to recover. They're very overlapping, which means that when you use EM and you compute the posteriors, it's going to be kind of really uncertain as to which cluster it should belong to because they're kind of overlapping. In this case, EM converges really, really badly, and you wouldn't want to use it. You'd want to use this like a direct optimization technique. In this case, you have the same number of clusters, but they're super well separated. In this case, it should be very easy for EM to say, I'm pretty sure you belong mostly to this, or mostly to this. Do you see how the posterior will be much more peaked in this example? In that case, that's where EM does like really, really well. It just converges super, super rapidly. So that's the intuition of that. And then just one other interesting note is, in addition to how quickly it converges, those 2 kinds of algorithms will also, if you have local optima, will converge to different places. And so in this example, they both start from here, and EM basically goes boom, boom to this local maximum. And the other method that they use, this sort of direct optimization, goes all the way here and then all the way here. And they get to totally different optima. So it's not even just about convergence. And then if you look at actually the likelihood, in this case, EM is doing much worse. So all that is to say is you may not want to use EM, you might want to use a hybrid, you might want to try both. Okay, so, and then just a little bit more comment on k-means versus mixture Gaussians. So if you take the 0 noise limit of the mixture Gaussians, then you essentially get back k-means. So that you kind of remove the probability and it ends up the same thing. And right, we mentioned this, that MOG allows non-spherical clusters via the covariance matrix, right? If I allow that to be non-spherical, then I get these elongated things. And because of that, it can be helpful in different ways. So if this is what like the original data say looked like, k-means, because it's not allowed to have elongated, is this the example? Yeah, I guess the elongated one that's spherical, somehow it's grabbing part of these points here. Whereas if you do EM, then it can actually get the correct shapes, then it's better to, it can more easily split them. So, right, and then I've said this already, but basically more importantly, the mixture Gaussians makes the assumptions explicit that you're using, and therefore it's easier to generalize and reason about, and you can derive the objective function and the algorithm in a principled manner. Okay, so that is EM. Now who can go code it? Not derive it, who can just code it for mixture Gaussians from today's lecture? Like a few, okay, it's like 2. Last time it was 0. Are there any questions? Does it make more sense than after last time? Who thinks it makes more sense? Who thinks it makes less sense? Who thinks it makes no more sense but the same? Still a few. Okay, all right. Sorry. So I'm going to kind of switch gears quite dramatically right now and go back to actually to some stuff related to classification. So if there are no question, yeah.
How do you know in EM that the alternate between these 2 like optimization sets actually is going to converge?
All you know is that it's doing maximum likelihood estimation, so you just know it's converging to a local optimum, and that's all you ever know in basically any, unless you have a convex problem, which is not common. I'd say most real machine learning models and cost functions that people use are not convex, and so generally what you do is you do multiple random restarts, and you see how sensitive is it to the different restarts, and you pick the best one. And if it looks like it's really sensitive, maybe you do more. So no matter how like rigorous and principled we present this, there's always an element of craft in the practice. So yeah, but you don't know. But of course, on the other hand, you don't know. But machine learning works really well a lot of the time. So, and part of like the difficulty of the practice of it is figuring out, is it working well right now for me, for the things I care about? And I think that takes a lot of hands-on practice. And so here we're trying to give you the core basics and expose you to a lot of the concepts and get some hands-on.
You're trying to do classification for something like amino acid recipes. It's like a bunch of amino acids. So like, what would it mean to like visualize that in 2 dimensions? Like when you add in the box here, because it's.
You mean like are you talking about the toy example of the mixture Gaussians with 1 dimension, or?
It's like right before, there's like some.
These?
Yeah.
Or earlier?
It's like these points are, it's just in 2 dimensions.
Yeah, this is just 2 dimensions.
The sequence is like 10,000.
Well, like DNA sequences are discrete objects, so you wouldn't use this. You would use, like, you could use a mixture of multinomials or something like that. So yeah, things can also get hard to visualize. So often, yeah, and that would be harder to visualize. I mean, technically, PCA you shouldn't apply to discrete data. There's analogs for like Poisson, but there's a difference between technically you shouldn't and everyone does. So yes, you can, and it actually does work well. And so you can totally do that. You could do dimensionality reduction on your data and then do clustering. That's a very common thing. Okay. Okay. So, because I actually just added this in, this next one, it's just a few slides because of a question I got after the last lecture, which was something about, I don't remember exactly, but it made me create these slides. It was like, are we putting something to do with one of the Gaussian discriminant analysis, was that like a ridge, like prior or something like, I don't know, but whatever it was, hopefully this makes it clear. So far in classification, we didn't discuss the kinds of things that we had in regression in terms of regularization and putting priors on parameters, right? We talked about prior probability of the class label, but we haven't talked about a prior on the parameters themselves, like the mean or the covariance or anything like this. And so, in contrast, for like linear regression, we did, right? Like we had this either ridge, which came from assuming a Gaussian prior and then doing map, which is some sort of prior on the parameter. And so I just wanted to emphasize that you can almost always do this in any kind of model. So we can do it also in classification, and you can also even do it in unsupervised learning, and we could do it for logistic regression as well. So just remember that this was the loss function for logistic regression, where P, this is the binomial likelihood, and P was the result of using the sigmoid of X times our parameter W. So we could add a ridge penalty here, and the effect of this would be that it's going to shrink the W's, and what that's going to do, it's going to mean that you get a flatter distribution over the classes. So you're somehow sort of less confident, would be the interpretation. So you can do it, we just didn't do it. And if you did that, then how would we do parameter learning? You can probably guess. We would still do gradient descent. It would just have an extra term in it arising from this. So
Is that kind of true with the bias over there?
you have to be careful with the bias. There's some people argue you should take the bias out of that. Yeah, but that's a good point. Yeah, so sometimes people won't put the bias term in the regularization, but you could actually. It's not clear. A lot of that depends on either what you believe about your problem or just what works better. And it's not clearly better. I mean, if I had to just guess like arbitrarily, I would pull it out myself. Because the bias term is really just somehow like a single number telling you about the like relative proportion of classes, and the odds that you're going to overfit that are kind of low. And so why do you want to somehow make it flatter? It doesn't make a lot of sense. Okay. And then we could also have done this for like the mixture Gaussians and Gaussian discriminant analysis. We could have added like priors on mu and on sigma and even on alpha if we wanted to. I'm not going to go in it. I just want to highlight that even though we didn't introduce these concepts in this part of the course, that these things are mostly plug and play. So that we could have added them here, and then we could have sort of tweaked our algorithms such that we're using the right, that we're using these. Okay, so now, how much time do we have? Okay, now we're gonna, this is also, I don't think this has appeared in any versions of this course, and I don't know why. I think it's actually really important, especially if you're gonna go do machine learning and classification. So this is about how you can compare classifiers, and there's something that's like really, really widely used all over the place in papers everywhere called ROC curves. And so I'm gonna try and give you, try to explain this to you. Okay, so imagine we had two classifiers. One was, say, a neural network. One was like a logistic regression, and it was a binary classifier, and we knew ones and zeros. Then how would you decide which of these two models was better? Accuracy. Okay, we can use accuracy. See, what accuracy? Just to be clear, do you mean count how many times it was correct? Like, did it get the 1 or did it get a 0? Is that what you mean? Yeah. Yeah, so how would I get a label from these numbers here?
Is that probably that class
It might be, it might not be. Logistic regression, it's supposed to be. Neural network, all bets are off.
Well, depending if that's the algorithm at sigmoid thing, that could be probably a big one here.
Okay, and if it was, okay, let's suppose for logistic that it was, then how do I get more than half? So what you're saying is, if it's a probability, if it's more than half, make it a 1, and otherwise make it 0. I think that's very reasonable. If it's not a probabilistic distribution, which actually there are many classifiers which aren't, we'll see a few of them in this class, then you can't do that. So you'd have to pick a threshold somehow, and then but you could pick some threshold, and then you could do that, and then you could count. Is it 1 or not, a mistake or not, and you could go through, and so you could do that. So that would be the number of misclassifications, which we call the accuracy. So this is actually really commonly done, and and the whole point of my giving this lecture is to tell you you probably never actually want to do that. And so for a number of reasons, one is there's just actually like a algorithmic problem is if this is not probabilistic, how do I pick the threshold? So that's already just one issue. And it turns out that even if it's probabilistic, you may not want to pick a threshold of 0.5. It's not clear. It's certainly intuitive, like I agree, like it's what all of us would say, but it turns out that that's not the case. And so some of the reasons you might not want to do that is it could be that the training data don't reflect the true class distribution at deployment time. Or sorry, actually this should just be the test. Well, all that is to say is that depends, that when you do that, it depends on the class distribution, and then that may not be representative of what you care about. And so also the accuracy doesn't really take into account whether the errors are false positives or false negatives, and that might actually be important. You might care about the different kinds of errors. And
we just made a hard encoding of the label we want. That's for example, one of them.
to do what? Say again?
So say you want to say 0, 1.
Yeah.
We have hard encoding of 1, 0, or 0, 1. Have our classifier cut it over there to like neural network. That's in the signal. We get even one.
Not sure I completely understand. It could, maybe you said something that makes sense, I just didn't completely understand it. So hold that thought, and you can ask me at the end if I don't address it. And so there's also sometimes people take some sort of mixture of false positives and false negatives, and there's this thing called F measures. I'm not going to go into the details because I don't think you should be using them. And then the other question is also like where, if you were looking at false positives and false negatives, like how do you even get a rate? Like which are the false positives, which are the false negatives? That depends on the threshold I use to make a decision, right? And so like what I'm going to now tell you is like let's think about how we use a trained classifier and about how some of these issues appear and how we can think of them in a nice way. So how would we use a classifier? So imagine that these are the distribution of scores of say some healthy individuals and some unhealthy individuals. And because there's some signal, these are different, right? If these curves lay on top of each other, it'd mean there was no signal in the classifier. So I could do, imagine this was the 50% here. I could just put a line here and I could call everything below it 50% and say these are all negative and these are all positive, right? And then I could go from there and I could do whatever it is I was trying to do with this. Maybe something to do with insurance or diagnosis or I don't know what. Okay, it's clear that like I get some score, might be a probabilistic score, it might not be, and I need to somehow put a threshold on it to make a decision as to what I'm going to do with each of these test cases, because this is the whole point of building a classifier is to go use it. Okay, is that, anyone have a question about this basic thing? Because everything's going to follow from this. Okay, so just some notation here. So if these are people in blue, these are the ones that, this whole blue distribution should be positive or unhealthy. And so the ones that are actually called that are going to be the true positives, but there's going to be some portion of them that are below the threshold, and we'll see what those are called. Those are going to, I mean, I've used some of these terms already loosely, but I just want to crisply define them because they're going to be very key. And those from the other distribution that lie above the threshold, these are of course the false positives. And those that lie below the threshold and truly are negative, those are the true negatives. And then finally, the ones I said is those that are positive but lie below the threshold, these are false negatives, right? So there's like basically 4 categories. 2 of them mean you got the right thing, and 2 of them mean you got the wrong thing. And so, right, just once we set a particular decision threshold, so in that example I just gave you, I put it like right in between, let's say 50-50, then from the decision threshold, we get an estimate of the number of each of these 4 categories. Is that clear? Like, but if I just have a probabilistic or classifier or some score, until I make that decision threshold, these things don't exist. I have to use the score in some way. And so, and of course, all my test points have to fall into one of these categories, so these all sum to n. And right, so the false positives and the false negatives are mistakes that were happened when we used the classifier, applied the threshold, and they ended up in the wrong bin. And the true positives and the true negatives are the correct decisions made by the classifier. And so there's this thing that it's also good to know about called a confusion matrix. So it's often summarized in a confusion matrix, and sometimes people even report their results this way in papers. These are a very common way to report things. And so, and in this case, this is the ground truth. So these are all the healthy people. All the healthy people were actually truly called healthy, or they were incorrectly called unhealthy. And so the total number of them is P, and I just, to get the number, it's the Tn plus the Fp. And similarly for the unhealthy. And so this tells you a lot more information than the accuracy, but it depended on a decision of a threshold, right? So if I knew the exact threshold I wanted to use, then this would tell me kind of a lot of what I wanted to know. But it's not clear that I should be using that 50% threshold at all, even for a probabilistic classifier, but without a probabilistic classifier, it's still not obvious that I should be using it. And just for those of you who take statistics, these 2 things, right, here I called it false positive and false negative. These are also sometimes, like in statistics, called the type 1 error and the type 2 error, even though no one in machine learning really uses those. And we're also going to talk about the rates. So I'm just going to extend the notion of true positive to the true positive rate, and that's just going to be dividing by the total number of positives. And that's sometimes called the sensitivity. So these are just kind of definitions. But so the true positive rate is really saying, among all the people who were really positive, how many of them got predicted as positive? And the true negative rate says, among all those who are truly negative, how many got called negative? And the false negative rate says, among all those who are positive, how many of them were false negatives? And similarly. And so also different fields like information retrieval versus machine learning use different names for some of these, which we'll see in a bit as well. But okay, so these are just definitions, but the main idea is that we have different kinds of errors we can make, right? Or non-errors. We can get things right in one way or another way, and we can get them wrong in 2 different ways. So let's go back to here. So I said that, like, what the number of these things are, false positive and null, it's going to change depending where I put this threshold, right? So if I shift it, I grabbed this from this website. I didn't know it was an animation. Okay, neat. It does what I think it does. So I can shift it around, and every time I shift it, it's going to change my false positive rate, right? Because the areas that I just showed you are all moving. So I think that's clear, right? I can just shift it like this. All right, so I liked it when it wasn't an animation. Okay, whatever, we shifted around, great. And every time we do, but it's clear that every time I shift it, I have another decision threshold, and the number of false positives, all these things completely change. And so the behavior of my classifier, even though I'm not changing, right? I'm just using one trained classifier here that has a real valued output, and I'm just showing if I use it differently, what the different behavior in terms of the errors are. Okay, and so, oh, wow, I didn't play this. Okay, I'm kind of, I don't know what's gonna happen in my own slides. Whoa, oh, interesting. Not what I expected. Hopefully it ends up how I want it to. Oh! Wow. I don't know what's going on. Whoa, it doesn't have the thing that I wanted. What? These bars, those bars. Okay, I'm gonna take it out. Now you can. Oh, now you can't see. I see. Huh. How do I? Wow. Okay. Oh. Where did this just go? What it's supposed to look like is to say that. I did off animations. Okay. Okay, what this is saying is that for every threshold, I get a different false positive and different true positive rate, right? I've just been saying that. But what you can do is, if you do it in the right way, you can trace out a curve where the axes are the true positive rate and the false positive rate. And this thing is called an ROC curve. So each one of these lines, basically, if I have the threshold as high up as possible, then I'm gonna call very few things positive. And so the false positive rate should be very low. So these bars here should just correspond to things with very low false positive rate. And as I move it closer and closer this way, I'm gonna call more things positive. So the false positive rate can only go up. There's this sort of monotonicity property. And this is how I can trace out the curve. I'll give you an exact algorithm in a second. But does it make sense to you that I can now, this is basically a trade-off curve, right? So depending where I set the threshold, I'm gonna trade off my false positive rate and my true positive rate. Because I cannot like kind of win on both of those. And how could I maximize the true positive rate? I could just call everything positive, right? And then, is that the right model? Yeah. So there's trivial ways you can maximize these, which are the two corners, but they're not of any use because you just call everything the same class and you only win at one. But there's an inherent tension between these, and that's the trade-off, which the ROC curve shows you. And so this is like now we're getting somewhere, because now we can think about the trade-off between these quantities that are very interesting as we were to change the threshold. So I don't know if I should put it back in presentation mode. And these actually have a long history. So these come from World War II, where they were first developed by electrical engineers and radar engineers for detecting enemy objects in the battlefields. But actually, in modern day sort of data analysis, they're used all over, and you'll see them a lot, especially in like medicine, radiology, biometrics, and other areas. These are really, really key thing in applications. Let's see if I can put it back in. Okay, so what's the algorithm for making this? Is we're gonna exploit the monotonicity of the decisions. And so I kind of alluded to that, of the threshold. So that property, what is this monotonicity of decisions? What do I mean? It's the property that if I have a particular test instance that's classified as a plus at some particular threshold, then if I move that threshold lower, it's still gonna be classified as a plus. And so I'll just give you a second to think about that and drink. So as a result of that, what I can do is I can sort the test instances decreasing by their scores, and I can just move down the list, and in between every two ones, I'm gonna say that's a new threshold. At that threshold, I'm gonna compute the false positive rate and the false negative rate, or what were the axes? I always forget the names, whatever the axes were. What were they? False positive rate and true positive rates, right? Yeah. And then, so you see that when they're ordered, basically just at the top one, I figure out, put a threshold there, I compute the number, and that gives me a point. And then I move down the list. And as I move down, I'm gonna trace this out. And this is actually kind of color-coded. So this is basically showing you how the threshold is changing. And as I go in between every 2 points, then it traces out this curve. And so it's actually really, really easy to compute these. So at each threshold, it gives me 1 point. And what's the most number of thresholds I could have? Someone tell me. The number of data points, that's right. So if I have only 3 data points and I do this, I can only get 3 points. Whereas if I have 1 million data points, do I necessarily get 1 million different true and false positive rates? I don't, right? They might be the same, but I could get, in principle, I could get 1 million. And so sometimes you'll see ROC curves that look really jagged like this, and it's because they have only like 1, 2, 3, 4 points. And then when you get to lots of points, they tend to look much, much smoother because the number of thresholds is limited by the number of data points. Okay, so what is this for again? So this gives sort of a more nuanced understanding than just the accuracy. And it's sort of a way to summarize and present the performance of binary classification models across all possible trade-offs in decision-making between the type 1 and type 2 errors. And it also happens to be independent of the class distribution in the test set. So whatever test set you give it, you could say double some of the points in one class and it wouldn't alter the curve. It would still look the same. So it also is nice. It's nice or not nice depending what you're looking for at the moment. And so you can compare classifiers by comparing their ROC curves. So let's take a look at that in a second. Right, but so first, right, just to say, like, can we do this for any classifier? So I think any classifier we'll see in this class you can do this for, which is anything that provides a real valued score. And usually in this class, we're gonna see probabilities are the score. But there are some classifiers where it just produces a 0, 1. And if you have just that, then you cannot draw these plots. Although you could do some weird things that are not even worth thinking about. So I should take out the bullet point because you should just never use those models. Okay, but so what are the kinds of, how should you think about it? So first of all, a diagonal on the ROC plot, this is like tossing a coin. This is completely at random. So you better never end up down here when you're, which is not to say, I promise you that if you go do research, one day you're gonna plot this and you're gonna end up down here because you have a bug in your code. And then so as you get a better and better, the perfect ROC curve is actually just this one point here where it's perfect. And then anything else is going to be these curves that kind of move away from it. And can anyone tell me if you had a point down here, then it's like, it's crazy, right? It's doing worse than...
off.
What's off?
The cursor.
Ah, thank you. For how long? Like 20 minutes? No, at least 5, all right. Thank you. At least one person's listening. That's good. Thank you. So what, if you were down here below, like imagine you had a classifier and you picked some threshold you're interested in and you ended up here, then like how is it possible you did worse than random? It means that there's actually a lot of signal in the data and you're just using it completely the wrong way. So can anyone tell me a trivial way to fix that classifier? Yeah? Just flip it, yeah, just flip the predictions. Where it was saying A, make it a B, where it was saying B, make it an A. But probably also go look at your code. Okay, so I think this is an easy question. So if this is, imagine you now have, you're trying different models on your data and you get these two ROC curves, both better than random, good. Which one should you use? I think it's obvious you should use the blue one, right? There's no ambiguity, great. So, and we'd say here that this blue curve completely dominates the red curve. So there's no setting, there's nowhere possible that we would ever want to use the red curve. So is it possible that we could compare models and that we don't have one curve that dominates? So yeah, it is possible. What's going on? Now my laptop's frozen. Huh. Wow. Well. Oh. All right. All right, that's interesting. I do not know what's going on. Let's try that again.
Windows outdated.
Oh, all right. But now I can't see anything. And then where do I have a cursor? Or a pointer? Okay, can I advance? Oh, okay, I can. Wow. Huh. Alright, this is not working. Okay, I'm gonna try once more, and then if not, I'm gonna call it a lecture. So I don't know. It's gonna reboot, and that's gonna take forever. Try once more. Okay, I'm gonna reboot it. If it's quick, I'll keep going. If it's not, is it working? No, it's just not. I gotta reboot the machine. Sorry. Doing the same thing. Okay, it's doing the same thing. So last 8 minutes, I'll take questions, and you go, oh, whoa, no, okay, I can't move it at all. Okay, class is over. Sorry.